VLSos here. This is a video lesson for geometry on slope. Slope is a very big topic in mathematics. There's lots of ways that we can represent it and think about the concept of slope. We start here with how slope is introduced in algebra. It's a property of a line. Lines have slope. And in algebra, we have the common equation for a line, y equals mx plus b, where m in that equation is the slope. So what I've started is, we're going to list the ways in which slope has been presented to us in a word. As a letter, m is very often used to be the letter or the variable that represents slope in equations in mathematics, like y equals mx plus b. And then we get to more of a conceptual understanding. Slope is rise over run. It's a ratio of two values, and we can call those rise and run to create that ratio. Rise and run have a little bit more descriptive or complicated terms. Rise can be thought of as vertical change. And run, horizontal change. To get an idea of what's changing, we'd have a concrete example of graphing 2 points on a line, so we have a line to look at. If we were to graph these points here, at 5,1 and 10,3, and then connect the points with a straight line. I'm going to do it as accurately as possible, which means that I need to graph accurately. These 2 points, the coordinates of the points that we were given, they're on a line. If we graph those 2 points and then connect them, we can graph the entire line. This line has a slope. And to find the vertical and horizontal change from algebra, a typical thing to do would be to start with 1 point and find your way to another point on the line by going over horizontally and then up vertically. And the amount that we had to go over horizontally is the run, and the amount that we had to then change vertically is the rise. And we can label this rise and run. Because this is done on graph paper and it's accurate, we could count boxes or sides of the boxes in order to get a rise of 2, and in this case a run of 5. The rise is the same thing as the vertical change. Vertical change is how much did you have to change vertically, up or down, when you went from 1 point to the other. We had to go up 2, so we have a vertical change of positive 2. Run is the horizontal change. How much did we have to change when we went from the same point to this other point? We had to go over horizontally at positive 5, to the right by 5. We have shorthand for vertical change and horizontal change, and that is delta y, where the symbol delta literally means change in, and delta x. And for this line, delta y, the rise is 2, and the run is 5, delta x. So we can calculate a particular slope for this line. There's another way to calculate slope without drawing the line and observing rise and run, though that's a very straightforward and easy way to do it. We can use the point information straight away in a slope calculation without needing to graph. And the way we do that is with the equation for slope. Often we say m is equal to the difference in y information of 2 points divided by the difference in x information between those 2 points. So we have a y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. There's complicated notation. Why do we have the 1s and 2s? Because we need 2 points. We have 2 points here. We can think of the x information as the first 2 numbers. So 5 and 10 is the x information of these 2 points. And because we have 2 x values, but they are different from different points, one's going to be x1 and one's going to be x2. Same thing for the y information. The y information is 1 and 3. We can label one as y sub 1, and the other is y sub 2. These are the values that we plug into this slope equation here. So in this case, the slope is going to be y sub 2 minus y sub 1, or the difference in y values, 3 minus 1, divided by x sub 2 minus x sub 1, the difference in x values, 10 and 5. And we can simplify the math. 3 minus 1 is 2, and 10 minus 5 is 5. It's the same slope calculation, of course. We knew the slope of this line is 2 over 5. But here we use the equation for slope. Now in geometry, what we've done so far is an algebra review. In geometry, we enhance our understanding of slope. In geometry, we call, when we graph a line and then we highlight the run and the rise as sides that create a triangle on this line. And this triangle is going to be a right triangle because the horizontal change and the vertical change, which are legs of the triangle, are going to be perpendicular to one another. That means they create a right angle here, and then the triangle is a right triangle with all the right triangle properties that we've studied. But in geometry, we have another way of thinking about slope, and that's the angle in this triangle that we call a slope triangle, because it's attached to a line and it helps us understand slope. It's got the slope ratio right there, 2 over 5. But it also has an angle in here, and we often use the Greek symbol theta to represent a measure of an angle. And this angle is also contains within the concept of the slope. It's how much the line is headed up. Well, the line could be headed down, and it would produce an angle that would go under this, or the line would be facing down, and the triangle would have an angle inside that would show us the angle was going down. But we have now 2 representations of slope. We have slope as the familiar rise over run, and we have slope as an angle. And they are not the same measure, but they're related. They're related because they both are the slope of the line, but it's presented in 2 different ways. Slope presented as a direction as an angle, and slope presented as a ratio of the sides of the triangle. Not the same value, but the same concept. And we can learn how to find the slope ratio given the angle, and find the slope angle given the ratio. We can go back and forth with these 2 measurements. We have a way of relating these concepts, and I'm going to spell it out. We could say the slope ratio associated with the slope angle theta. This is an odd way of spelling it out, but you'll see why I'm organizing it this way in a moment. So what I'm starting to talk about here is I want to find a way to relate mathematically these 2 ways of thinking about slope. The slope ratio is the familiar rise over run, and the slope angle is this new way of thinking about slope. So I have the beginning of a relationship. The slope ratio associated with the slope angle theta is opposite over adjacent. Opposite over adjacent from what? Well, the opposite and the adjacent that we're talking about is the sides in the right triangle that is opposite the slope angle that we're talking about. In this slope triangle here, if we've labeled the slope angle theta, then what's opposite is the side in this direction. It's going to be the rise. And what's adjacent, adjacent means next to, but not the hypotenuse. Adjacent to this angle here is the one that's next to it, this side, which is the run. So I've organized this relationship between the slope ratio and the slope angle in this odd way because we have a shorthand way of presenting the same information. These words here and what they mean are captured in a word called tangent, abbreviated TAN. The angle is still theta. The word is, we translate to an equal sign, is, equal. And opposite over adjacent means a ratio. And we can have abbreviations OPP for opposite and ADJ for adjacent, just to shorthand it. So I've translated this conversation into an equation. And this is a very common equation to use in mathematics. We have this special word, this special concept, tangent. Tangent means the relationship between the slope ratio and the slope angle that you're going to take the tangent of. This is new information, but let me show you how to use it. Let's create another example. I also need a calculator. In this example, we're going to have a line. And we're going to work with an approximation. I'm not graphing it on the grid because I don't mean to be precise. I'm starting with a line, and I created a slope triangle on that line. It's a right triangle that has a rise and a run. Those are the legs, but we don't know the values of the rise and run. What we have is the slope angle, 23 degrees. This line is heading up at 23 degrees compared to the flat horizontal. So we know the slope angle. And what we want is the slope ratio that we're used to. We don't have points to work with this time. We just have the slope angle. We're going to practice using this relationship. So this relationship means that the tangent, meaning the slope ratio that we're trying to find, associated with the slope angle that we know to be 23 degrees, is equal to the opposite over the adjacent side. Tangent of 23 degrees. There's no variables there. That's something that a calculator can give us. We have a key on the calculator, tangent. And the way we use it is if our calculator is in degree mode, for this calculator, we enter the degree amount, this slope angle, and press that tangent key. And in this case, what we're going to get, we're going to write down 0.424. That's an approximation because we got an irrational number. So we're working with an approximation. But, yes. And this is equal to opposite over adjacent, which may be a little bit confusing because we have an approximation, but it's equal to what's supposed to be two measurements, an opposite and an adjacent side, a rise and a run. How does this one thing equal the ratio of two things? Well, let's remind ourselves that we can represent this as over 1, 0.424 over 1. And we get our slope ratio. This means that for every change in 1, that would be a horizontal change of 1, we get a rise of 0.424. So if we go over 1, we go up 0.424. That's a slope ratio. It's not a familiar one. It might be a little more helpful if we multiplied this by 5 over 5. It might look a little bit more familiar to the triangle that we were working with. I have my ratio. I multiplied by 5 over 5. I got 2.12 over 5, and I'm thinking of this as a slope ratio. And if I do, I think of this as a rise over a run, which means that if I run 5, if I change horizontally by 5, then I go up 2.12. And thinking of it like this, looking at it with these numbers, it kind of matches the triangle that we drew off this line. This run is approximately 5. And when we run 5, we expect to rise 2.12. So it should intuitively work out. So what did we do? We did a new thing. Remember, there is 2 ways to think about slope now. As a ratio, rise over run, and as an angle. And they are mathematically related. If you know one, you can get the other. How do you do that? With this concept of tangent and a calculator. Tangent means that you are trying to find the slope ratio that is associated with the angle that you take the tangent of. We had a triangle, we started with an angle, a slope angle of 23 degrees. And we set up the equation. The tangent of 23 degrees will be equal to the slope ratio, opposite over adjacent. A calculator told us the approximation of the tangent of 23 degrees. And that was our slope ratio. We had to convince ourselves that something like that could be a slope ratio by reminding us that we could put it over 1 in order to turn it into 2 numbers that have as a fraction. And then we multiplied by 5 over 5, which is a version of 1, so it can be done, into a ratio that made a little bit more sense with the triangle, the visual that we started with here. So we can be confident that it works. We need practice with this new information.